Everything in Python is an object. And in the next couple of videos, we're going to talk about this idea of OOP, or Object-Oriented Programming. What it is, what it's useful for, and why it's such an important topic for us to become great developers. Now, when I say everything in Python is an object, what do I mean by this? Well, remember our data types that we've talked about? If I click Run here, you'll see that we have all our data types, but we have this class keyword in front of it. And I mentioned previously that this is something that we're going to get into. Now, everything here is an object because in Python, everything is built by this class keyword. And we're able to use different methods on our objects like this to perform some actions on them. So what is an object? Objects have methods like these and attributes that you can access with the dot method. Now, object-oriented programming allows us to go beyond what Python just gives us, which are these data types. But wouldn't it be amazing if we can create our own and make Python even more powerful? And using object-oriented programming and what we're going to learn, the class keyword, we're going to be able to do just that, so that the list over here can grow to our own custom objects. Now we're going to explore this topic of object-oriented programming, what objects exactly are, and what this class keyword is over the next couple of videos. But the key takeaway is that we're able to create our own types, our own data types, with different attributes and methods. Now, why is this useful? Let's have a look at an example. Let's say we're working for Amazon. And Amazon recently decides that, hey, you know what? We're going to have delivery drones that are going to deliver our customers' packages a lot faster. But we need to code this drone, right? And up to this point, we've learned that we can do that with basic functions, conditional logic, and just writing our code on a .py file. But the problem is, as code gets bigger and bigger and bigger, it's not just one file. It's not just 10 lines of code. It becomes hundreds and thousands and millions of lines of code divided into different files. Code gets more and more complicated because we live in a world where technology is everywhere. And programming something like a drone is quite complicated, especially when it's a delivery drone. So how can we use object-oriented programming to make this code more manageable? Well, OOP is what we call a paradigm. That is, it's a way for us to think about our code and structure our code in a way that is easier to maintain, extend, and write. So if we're writing a program about, let's say, that does drone delivery, well, we break it up into small pieces, into little objects that represents the real world. For example, I might code an object, my own data type, which is the propellers that allow the drone to fly. And maybe another developer works on the camera and the vision part of the drone. Another developer can perhaps create the claws that hold the package. And then another developer might be able to work on the signaling so that we're able to send signals from our drone to, let's say, Amazon headquarters and know where all our drones are. What we're doing here is we're breaking up functionality and data into different pieces that model the real world, into separate objects, so that different people can work on different parts and then we can just combine them afterwards. And the beauty is when we want to, let's say, create a delivery system that's not a drone this time, well, it's a tank-like delivery robot. We can use the same pieces, such as the camera and the claw and maybe the signaling, but we can just remove, instead of the propellers, and use the tracks that, let's say, tanks use. And somebody else can code this part. But we're able to use different pieces, extend functionality from our drone into different objects. Now, if you still don't understand 100%, don't worry. We're going to go over this over and over throughout the next couple of videos. The main takeaway is that OOP is a paradigm, a way to think about our code, a way for us to structure our code so that as it gets bigger and bigger, we're able to be organized. Because we're not writing silly 10-line codes. We're writing millions and lines of codes. Companies like Netflix have thousands of developers that are writing code every single day. They need a way to structure and organize this code so that, well, it just doesn't turn into complete chaos and complete spaghetti code. Let's take a break and learn more about OOP in the next video. In the previous video, we learned that OOP is what we call a paradigm, a way to think about our code and structure our code. And I'm going to link to this excellent article from Wikipedia about the history of programming languages. You see, we started with basic programming languages. We had things like assembly language that was really low level, really close to machine code. We had things like COBOL. And then we slowly, as we started writing more and more code in the 60s and 70s, we started establishing some of these fundamental paradigms. And one of the big paradigms that came to be, especially with the Smalltalk programming language, was this idea of object-oriented programming, or an object-oriented language. You see, up until that point, we wrote what we call procedural code. What that means is that if we look at a Python file, for example, a procedural code was just like a procedure. We simply had lines 1 through, let's say, 100, and we just went from the top of the line to the bottom of the line. We had conditionals, maybe loops, but everything was do this, do that. It was us telling the machine, hey, just do exactly this, what I'm about to tell you. With the introduction of object-oriented paradigms, this changed a bit. We started saying, hey, let's model something in our code that represents a real-world object. For example, if I'm about to code a car, I would create a car object that has data on what color it is, what type of engine it has, how many seats it has, but also actions like methods that we can take on it, such as the car can go forward, it can go backward, it can open the door. And instead of having these line-by-line procedural code, we can think in terms of models, real-world blueprints. Because as humans, we organize things. Think of a room, think of a factory. By organizing things and having different groups in a specific location working together, that's a better way to think as well as to run things. So how would this look in Python? Well, Python is an object-oriented language, or can be, which means that it's able to support OOP ideas, this idea of objects and modeling. And we've seen this when we use the type. We see that everything is an object because we use this class keyword. But what is this class keyword? In Python, I can create my own data type, my own class, by simply saying class. And then afterwards, I can name it whatever I want. Let's say class big object. Now, right away, you see here that the naming convention is different than what we've seen before. We're going to make sure that it's capitalized, which is the standard. We want to let programmers know that this is going to be a class. And we're not using the snake case, we're using what we call camel case, which is every new word is a capital letter. And then here, we use the colon, and then in here, we write our code. Now, I'm not going to write the code right now. I'm just going to pass, but right there, I've just created a new class so that if I do, let's say, for example, type big object and I click run, well, I still get type because right now what we've created is this class, which is a blueprint, but we haven't actually created the object. I know the wording can get confusing, but bear with me. I will explain this. We can now create, let's say, object1 equals to big object, and then run this class. So that if I do type object here, object1, and I click run, I get class big object. You can ignore the main here for now because we're going to talk about it later. But you see here that I've just created my own object. Now, let's think about what just happened here because it is a lot to understand. You see, in object-oriented programming, there's this idea of a class and an object. Now, a class is this. It's the blueprint of what we want to create. What are the basic attributes, that is properties, that our class has? What are some basic methods or actions that our class can take? And then from this blueprint, I'm able to create different objects over and over using this as the building block. So this blueprint is what we call a class, which we define with the class keyword. And this class can be instantiated, that is the action of creating different instances. And what are these instances? These are all objects. Now, the naming here is something that you're going to have to get used to, and all object-oriented programming languages have this language. So you'll just have to understand when somebody says, hey, I just instantiated a class, it means, hey, I just created a new instance, a new object. So looking at this diagram, let's go back to the code that we just wrote. We've created here a class or a blueprint. And then here, this double bracket is us instantiating the class and saying, hey, class, use whatever you have code in here and instantiate it and create a new object. So we're creating a new object by instantiating this class. And this is exactly what we're doing with something like a list, right? I can create multiple lists over and over and over. And every time I create a list, I have access to all of these methods and sometimes even attributes that I can use. And this way, I save a lot of time instead of coding it myself. And in the same way, I can create multiple objects here. Object 2, object 3, just like that. And now I have 3 different objects that I can use based on this blueprint. Now, the blueprint right now doesn't have anything because, well, I can add code here later. And we're going to do that in the next video. But the beauty is, let's think about efficiency here. You see, the blueprint itself, the class, is going to be stored in memory. So Python interpreter is going to say, hey, big object, it's going to be the blueprint for this. So I'm going to store all that code in memory. But every time I create an object, I don't have to rewrite the code or do anything like that. I can simply say, hey, go in memory to where big object is and just run that code. So that, again, we're keeping our code dry. We have one place that allows us to instantiate our code into objects. Let's take a break and expand on this class in the next video. Now, the best way to learn is to actually see code in action. So enough theory, let's actually code our own class. I'm going to just delete everything and start from scratch. And let's say that we're working for a gaming company. And this gaming company has, well, this wizard game that they want to create, almost like Harry Potter. Now, how can we think about it in object-oriented programming? Well, the first thing that we're going to need is we're going to have players, right? Each player has a character that they need to play. So let's create a class here and call it player character. Again, notice the naming convention because it's a class. And another rule is that usually you want it to be singular, not plural. So you can't say player characters because, it's a blueprint. From this blueprint, we're going to create many characters, but those are going to be objects. So player character, single, in singular. Now in here, I'm going to do a few things. And I'm going to warn you, this is going to look confusing at first, but bear with me. I will explain it. We're going to define a underscore underscore init underscore underscore. Now in here, we're going to say self and then give it a name, the name of the character. From here, we're going to do colon once again and simply say self.name equals to name. Oh boy, what just happened here? Again, I'm going to hold off explaining what this does and just write a few more lines of code so that it makes a little bit more sense. I'm going to write another method in here, and I'm going to define, let's say, a run method that each player can run. And in here, I'm going to once again have this weird self word, and then simply inside of here, say print run. All right. So I've just created this class. It's still kind of confusing. We don't really know what this init is, what this self is, and this whole new look. But let's ignore that for a second and simply say player 1 is going to equal player character and instantiate that player so that we can print player and see what's up with this player. If I click run, all right, I get an error. It's a type error. It says init missing one required positional argument name. All right, let's take a break here and see what is happening here. You see, this init method is a special method. You see the two underlines here? This is called a dunder method or a magic method, and we're going to have a video specifically about this. But when we're building a class, you usually see this at the top. And this is what's often called a constructor method or an init method. And this is automatically called anytime we instantiate. Remember, instantiate means is we're calling the class to create an object. So when I do this, it's going to automatically run whatever is in this code block. So when I run this, you see that I'm getting the error on line 9 right here. On line 9, when I try to instantiate the player character, it runs init, and then it tries to do self.name equals to name. But the problem is that I'm not giving it an argument name. And that is because when we call init, we accept whatever is after self as the parameter name. So we need to give it a name of this character. So let's say the name is Cindy. If I click run here, all right, it looks like I have a player character. And as a matter of fact, it even shows me that it's an object at this memory location. So on our computers, this is where the player character, player 1, is located now. Very cool. But what is this self keyword? And what is this code on line 4? This is a way for us to define, well, self. Self refers to the player character. It's saying, hey, this is going to refer to this player character that we're going to create, player 1, and I want self.name to equal whatever the parameter name is. So that if I do player.name here and I click run, I get Cindy. And why is it Cindy? Well, because I gave it the parameter, player character, and when I instantiated it, I passed the name parameter. The default parameter is self when I do init. And in classes, you see here that the default, always the first parameter when we're defining a method, is self. And now I give name to self.name. What if I remove this here and I click run? You see that it says object has no attribute name. Because in order for me to say, hey, I want player to have a name, I need to say self dot. Because self refers to player 1. So if you remember, when we had a list, we had to do dot and then we would say append. Well, somebody wrote this append code. And in the append code, it's going to say self dot, let's say, add to the list. And self refers to whatever's to the left of the dot. So this way, it allows us to have a reference to something that hasn't been created yet. In this case, player 1, and let them know that, hey, when it's created, when we instantiate, then I want you to make sure that player 1 has this name attribute. So that if I create another player, and player Tom is going to be player 2, if I print player2.name and I click run, I have 2 different players with 2 different names. I was able to use the same piece of code, but have different values because the self, every time I instantiate this, refers to first time player 1, then second time player 2. Now, self is one of those things that gets really, really tricky to understand. And you might need to watch this video a couple of times. But the key here should be evident to you. That is, I'm able to write code only once. Remember our principle, dry, do not repeat yourself. And I'm able to make it dynamic by saying this data that we're going to create for the object is going to be dynamic and it's going to change based on what we give it. So that I can create different players with different attributes, but still use the same code. Now, I can have multiple things here. I can have age, for example, and once again, I can say self.age equals age. And then Cindy will have to pass, let's say 44, and Thomas 21. So that here, once again, if I do age, they'll have different attributes. So remember, these are attributes or properties that these objects have. And you can access them by doing the dot notation and then accessing the property itself. You see that I don't have any brackets here because it's not a method. It's not taking action. It's simply saying, hey, I want to access this attribute. If I do dot here, my editor will actually tell me and will have the symbol for, hey, you have access to the attribute age and name. And as a matter of fact, I also have access to run the method. So that if I click run, well, remember, a run is a method. So I get this bound method, but it's not printing anything. It's not taking the action. So we have to, once again, add the brackets, hit run, and look at that. I'm able to do run, then I get none, then 21. Why do we get this none? Because remember, this is a function that doesn't return anything. When a function doesn't return anything, what do we get? We get none. So maybe I can just say return done. If I click run, there you go. We have run, done, 21. Now, one last thing before I end this video. The interesting thing here is if I do player 1 and then player 2, and I print this, and I click run, you'll see that I get the player character, but the object, each of these objects, player 1 and player 2, are at different memory location. So I'm able to use one piece of code, one blueprint, to create multiple players, but these players are not the same. They're created from the same blueprint, but they live in different places in memory. And that makes sense, right? We don't want Tom and Cindy to be the same player. They're 2 different players. So this way, we're able to keep things safe. And anything I add to player 2, for example, let's say player 2 can now attack. And attack will just be a property that will be 50. Now, if I do dot attack here, you see that player 2 has attack. But if I do player 1 dot attack, I'll get an error. Object has no attribute attack. I hope you're starting to see the power of classes. Although it may be difficult to understand at first, the power becomes evident when we are able to create this blueprint that we can now use over and over and over to create our own objects. Let's explore more in the next video. Object-oriented programming allows us to create objects that have their own methods, like run, and attributes, properties. It's a great way to add more functionality to a language and mimic the real world. For example, we use the idea of working for a gaming company. Although Python only gave us a few data types, I was able to create a player character. And now my boss is happy because this player character can be used all over the game. And all other coders have to do is run this line with the custom name and age of the character. So OOP allows us to write code that is repeatable, well organized, and also memory efficient, right? Because we only write this once. So if you want to be a great developer, OOP is something that you need to know and you need to understand because, well, this is how you want to organize your code. Thinking less procedural and thinking more in terms of functionality. Grouping data, like attributes, together with methods to create this class that is able to mimic something from the real world. Now I want to show you a useful tool here. We saw that when I do player dot, my editor shows me what I have available. The properties, as well as these purple boxes, which are the methods that I have available. And right off the bat, you see that I have age, name, and run, but then I have all these other ones that I got by default. Now, these are all dunder or magic methods, which we're going to get into. But the key here is that if I do something like help, which is a new function that you may have not seen before, and let's comment this out. If I click run, I actually get, well, the entire blueprint of the object. If I do something like a list and I click run, again, it shows the blueprint that it has. And this is a great way to see what class blueprint some of the Python data types have. Now, this is something we'll revisit later. But I want to go back to this player character. Now, in here, we saw that we're able to create attributes. And attributes are pieces of data that are dynamic. That is, when we instantiate an object, they are going to be unique to that specific object, like name and age. And we had to use this self keyword to make sure that it was dynamic. However, there's another thing called the class object attribute. And it might look like this. Let's say we had the player character and they had to, let's say, be a paying member. In order to play this game, you have to have played, or you have to have gotten a membership. So let's have a membership equals true attribute. Now, unlike this one, you see that it's on the same line as our methods, and this is called a class object attribute. And a class object attribute, unlike these regular class attributes, is different because, well, it's not dynamic, it's static. So if I click run here, and we want to make sure that we print something, so let's print player 2, and I click run. Well, I get the player, that's great, but if I do dot membership, and I click run, look at that, I get that equal to true. If I do player 1 here as well, and I click run, I get true again. So all the players have membership set to true, but this is not dynamic. It's a class object attribute, which means it's an actual attribute on this class. And this is something we use when there's no change. This is going to be true and exist for all objects. So you can't really modify it. It's just all the objects that we instantiate will have access to it. So this doesn't change across instances. And we can use this down here as well, or anywhere in this class blueprint, as a matter of fact. For example, let's say we wanted to check if membership exists. So we're checking if membership is true, which, I mean, it always is, so this is a little bit redundant. But in here, I can say only if membership is true, then I'm going to assign name and age. But in order for us to access membership, I'll have to do self.membership, because remember, self refers to this player character, so that if I run this, everything still works. And if I do player1.name, this still works. Or I can refer to this by the actual player character. So player character.membership. So if I click run here, this also works because it's a class object attribute. If I were to, perhaps in the run, let's change this to shout. And in shout, it's going to want to run. Let's remove this line. It's going to print an F string that says, my name is, and give it a name. Do you think this will work? Let's give it a try. Let's say shout and make sure we run that method and then click shout again. If I click run, I get an error. Name is not defined on line 11. If I go to line 11 here, name is not defined. Why is that? Well, because we haven't used self. So let's do self.name. And if I click run, there you go. My name is Tom. My name is Cindy. Okay, awesome. And I'm able to use self because I pass it into here as the first parameter. And all methods receive the first parameter as self so that we can use them. But could I just do player character.name? If I click run, I get an error. Player character has no attribute name. Now, why is that? Because name is not a class object attribute. It's not actually a property or an attribute of player character. No, it's defined in our constructor function, our init function. So that's a bit of a gotcha here, and something that you'll have to get used to. A class object attribute is something that doesn't change across different instances, versus an attribute or a class attribute is something that is dynamic and specific to each class object. The way we access them is different, where we can actually access membership like this, but in order for us to access a name or age anywhere inside of our class, we have to use the self.name, which is why anytime we create a method in a class, even if I create a new one over here, and let's say this new one is going to be run, well, once again, I have to use self as a parameter, and then anything else that I want to add in here as the second parameter, so that when I click, let's say, run, I pass in the hello argument like this. I know this is a lot, but hopefully you're starting to follow the rules of classes. Once you remember these rules, then it becomes easier and easier. But we'll practice this a little bit more in the next video. I want to add a quick note about this constructor function. Remember, this gets called every time we instantiate an object. And this is how we create custom objects, right? But an interesting thing that you can do here, because you have control over how the instantiation happens, you can do different safeguards. For example, let's remove this for now because we don't need it. Or actually, let's change this to, let's do age. We want to check if the user is over 18. Then we're going to run this. Otherwise, well, the program's going to error out because we only let people age 18 and over to play the game because let's say it's rated R. So we can do different things in the constructor to make sure that we are instantiating the object the proper way. We can also give default parameters, like name can be anonymous if we wanted to, if they don't provide a name. And then age will be, let's say, 0 if they don't provide an age. So that here, let's say I forget to instantiate player 1 and player 2. If I click run, I get an error. Player object has no attribute name. And this is on line 11. Now, why do we not have self.name? Well, because on line 17, we were trying to call shout, but unfortunately, we never instantiated this because when we don't provide anything, the age is going to be 0. So we're never going to instantiate with these properties. Okay, so let's just give it Tom, and then age is going to be 10. And let's just remove player 2 for now. If I do player 1 dot shout and I click run, once again I get an error because, well, Tom is only 10 years old. We're not going to create this character. Now, we're going to talk about errors, and maybe instead of just having this error out, we can send a message saying, hey, player is not old enough. But for now, I hope you see the power that comes with this idea of constructor and the instantiation of an object, where we're able to add these different controls and safeguards to perhaps make sure that we receive the right data type in order to create the object. Or maybe the age is over 18, in order to make sure that when we actually instantiate this player 1 object, we're doing it the right way. So this init gives you a lot of control. Welcome back. We learned that we're able to create an actual attribute for the class. But what about a method? Is there a way to do something like here where we deal with attributes, but for methods? Well, there is. And we use a decorator, which is a topic that we'll cover later on, and you'll understand how these work underneath the hood in a bit. But for now, the syntax that we're going to use is the @ sign, and then we call a class method, like this. And now, with this decorator, we can now write a function. For example, let's create a function, and we'll call it adding things that will take num1 and num2. And in here, make sure we add the define for the function. And in here, we'll just return num1 plus num2. Okay, so what does this class method do? Let me minimize this just so we can see a little bit better. Now in here, let's see if player 1 has access to adding things. So let's just say adding things 2 and 3. If I click run, it takes 2 positional arguments, but 3 were given. That's on line 17. So when we call this, we gave it 2 parameters, but then it was expecting, it says that we actually got 3. And that is because adding things, the first parameter, just like we have here, is the CLS. And CLS stands for class. So this player character, that's the class that we're referring to. So similar to what we've seen before, but the standard is to use CLS. Now if I run this, you'll see that we get 5. Okay, but looking at this, it looks like it's pretty much the same as the above, except instead of using self, we use CLS. But how is this a class method? Well, it's because we can actually use this without even instantiating a class. Let me show you. Let's say that we don't instantiate player 1. And now I just simply call in here player character dot adding things. If I click run, look at that, I get 5. It's a method on the actual class. It's a class method. So you can do some interesting things. And by the way, class methods aren't used as often. So if you're thinking, why do we even need this? Well, I would say 95% of your classes aren't going to use something like a class method, but there are cases where this might be useful. For example, we can use the CLS to actually instantiate an object in here. So for example, I can say that CLS, which is the class, which is the player character, and I'm going to instantiate it, remember, just like we did here with the brackets, with num1 plus num2 as the second parameter, and we'll give it name Teddy. If I hit run here, look at that. I've instantiated an object, Teddy, with the age of what should be 5. So let's take this, make this equal to player 3. And if I do player 3 right here, dot age, and I click run, I get 5. So I have a whole new player here that was created by using this class method. So I was able to create, just like I created a class object attribute, a class method using this @ sign. There's also one other way of doing something like this, which is the static method. And the static method works the exact same way as here, except you do not have access to the CLS or the class. So you can't do something like we did above. Instead, we just perform some sort of method, like adding things to like this. So the only difference between the two is the idea that we don't have access in our parameters to this CLS. So we would use something like static method where we don't care anything about the class state. A class state is something like these. We don't care about the attributes, really. We use something like a class method when we do care about these attributes and maybe we want to modify them or change them. Now, these class method and static method is something that you won't see very often, but I wanted to show it to you just because you might encounter it through your Python career. Hopefully this wasn't too confusing. In the next video, I want to review what we've just learned up until now. Welcome back. Up until this point, we learned that OOP, or object-oriented programming, is a paradigm, a way for us to think about structuring our code. We went from procedural to writing functions to now using things like object-oriented programming. Now, what we've seen is what we call a classical OOP. That is, we use classes to incorporate object-oriented programming paradigms. We learned that we can create a class in Python with a class keyword using this naming convention, which is camel case with capital letter, which tells other programmers that this is a class that needs to get instantiated. We learned about class object attributes. We learned about how we can instantiate an object and how we have this init function that runs on every instantiation to customize our objects. We learned about how to add methods to our class so that each object that we create and instantiate has access to these methods. We also learned that there's things like class method and static methods, which are methods that can be called on the class without actually instantiating it into an object. And all of this was that so we can create our own data type that models the real world. Now, there's still lots more to learn in object-oriented programming. But if you follow these guidelines and look at this overall structure, that's pretty much it. That's how classes work in Python. And we actually have gained a really powerful tool now to really make our code better. Now, the idea of object-oriented programming requires some practice, and it's really hard to grasp when you're just starting out. We're going to try and do some exercises and learn a few more things about object-oriented programming so that we can really grasp this concept and use it in our everyday programs. I'll see you in the next one. Bye-bye. Welcome back to another Developer Fundamental. What is it? It's to test your assumptions. What do I mean by this? Well, anytime you learn something new, maybe something I'm teaching you or something other instructor or book or resource is teaching you, you want to test your understanding and your assumptions. Because you don't want to have any magic black box that things are happening that you don't understand. You want to know how things are working so you can explain it to people. For example, remember how I said that self is referring to this player character class? How can we test this assumption with code? Well, if I had just learned what self is, what I would do is to say to myself, well, I want to see self. I want to know what it is. You know what? I'm going to return here self and actually see what's going to give me, right? It's code. I can return self if I want to. Well, let's do that. Let's create this player character. Yes, I'm 100 years old. And then here we'll do player.run. Let's do a print here and click run. All right. So the self is the player character that I created, which is player1, which is located here. Okay. So although this is a simple example, what I'm doing as I'm learning is to test my assumption. Is that what I expected? Before I even run this code, I like to think in my head, what do you think is going to happen? And if there's a mismatch and I get something returned that I don't understand, well, then maybe I look into it. For example, this __ main. I still don't really know what this is. Why is this here? I mean, it has to be there for a reason, right? And that's something that we're actually going to talk about later on in the course when we talk about modules. So hang in there. But the way that learning happens in an accelerated fashion is when you don't just take my word for it. Because if you do that, you don't fully grasp the concept. The idea is to test and test yourself as well and your understanding. And say, if my assumption is that self is referring to the object that we create, how can we test it? And this is a great skill that a great programmer has. So hopefully, in future lessons, when I'm teaching you something, you test those assumptions. You test your learning through methods like this. I'll see you in the next one. Bye-bye. Welcome back. What I haven't told you is that when learning about object-oriented programming, again, and not just in Python, but in any programming language that supports OOP paradigm, is this idea of 4 pillars of OOP. The 4 things that object-oriented programming does really, really well. And as a matter of fact, we've actually learned the first one. And that is the idea of encapsulation. What is encapsulation? Encapsulation is the binding of data and functions that manipulate that data. And we encapsulate into one big object so that we keep everything in this box that users or code or other machines can interact with. And this data and functions are what we call attributes and methods, right? We're able to encapsulate the functionality of a player character by having name and age data or attributes, and also have functions that can act upon this name and age. So for example, I can have a method in here that says shout or speak. And this speak method can now use the name and age. I can say, my name is self.name, and I am self.age years old. So that if I do player1.speak and I run this, my name is Andre and I am 100 years old. I'm encapsulating the functionality. If I didn't have this class, I would have, well, some variables and then 2 functions. But by using encapsulation, I've packaged this up into a blueprint that I can create multiple objects of so that when other people see my code, they know, hey, this is an entire object that I can interact with. I can use in certain ways that player character describes. And we've also seen this in our built-in Python data types, right? When I create a string like this, because of encapsulation, I have all this functionality available to me, all these methods that I can access. So that if I do, let's say, capitalize, it will capitalize all my strings. I have all this functionality encapsulated for me to use. Now, why do we want to package data and functions into attributes and methods? Well, because this gives us extra power, right? If, for example, this player character doesn't have any actions, any methods, and just had attributes, well, in that case, this is kind of like a dictionary, right? It's kind of useless. If I print player1 here, and I click run, I have this player object, but I can access name like this, and I can also access age like this. But I can't really do anything to it. I could have the same dictionary here, let's say player2, that is going to equal a dictionary that has name of Andre and then age of 100. And the only real difference between the two is the way I access this information. Instead of the dot notation, I use the bracket notation to access the keys. So that when I click run, I have to make sure that I do 2 here for player 2. If I click run, again, it's the same thing. Sure, I can do it this way, but it's kind of useless. Why not just create a dictionary if all I want is data? But using this way, I'm combining things, packaging things up into those instances, into those boxes that can be useful. And also things that have meaning, right? Because our world is full of data and actions, right? Even a tree. For example, if we had a tree class in our real world, the tree would have maybe whether it was an evergreen or a perennial. It'll have whether it has leaves or it doesn't, how tall it is. It'll have all that information, but also actions, right? I can cut down a tree, the tree can grow, the tree can extend its roots. So this way, we're able to mimic what happens in the real world with our code. So that is encapsulation, and we've seen it. But let's talk about our second pillar in the next video. We know that there's 4 pillars of OOP, and we learned about encapsulation. What's the second one? Well, it's called abstraction. And abstraction means hiding of information or abstracting away information and giving access to only what's necessary. So whatever the user or the programmer or the machine is interested in, that's the only thing we give access to. Everything else, we kind of hide it in a blanket underneath the hood because our users don't have to worry about it. Let me show you what I mean. If I go back to our old example here, so instead of having a dictionary, we actually have a player character with a bunch of methods. Now, abstraction can actually be seen here, right? When I do player1.speak, you're seeing abstraction in action. Because when I click run, I get this string, but when I call speak, I don't really care how speak is implemented. All I know is that player1 has access to the speak method, and I can use it. Same with when I'm using something like a tuple, right? If I have 1, 2, 3, and I do dot here, I can do count to count how many items are in the tuple. So if I do print and click run, well, I have to give it a thing that we're looking for. In our case, let's look at 1, and let's add another 1 in here. If I click run, I get 2. Now, do I need to know how the count method was implemented? No. I mean, I can go look into it. I can look at the Python documentation, maybe the Python code, and understand how it's actually counting this, but I don't really need to, right? If we try to understand every single little piece, our head's going to explode. Sometimes all we need is a method or an attribute and just get access to it without having to worry about how it's being implemented, which is really, really nice. The same goes with built-in functions, right? If I do length here and I click run, I get a length of 4, but I don't really need to know how length was implemented in Python. It's abstracted away from us. And this is the power of OOP. It abstracts away things that we don't need to care about, or at least it makes us more efficient so that we know that it works a certain way and we're not wasting our time learning or coding from scratch. If we had our iPhone, for example, well, the camera feature on an iPhone, it'll be nice for an app that we build to use it, but we don't need to actually know exactly how the iPhone camera is coded on an iPhone. No. Instead, the iPhone usually gives us a way to say camera.take picture to actually allow us to take a picture without knowing how the Apple engineers actually coded the camera. So it's a very powerful concept. Okay, so you're thinking, I think I get abstraction, but let me ask you this. Could I just do player1.name equals to, let's say, exclamation marks, and then player.run? Or you know what? Let's do speak equals to boo. Make sure it's player1. Well, if I now print and do player1.speak, and I try to run this function, let's see. I get string object is not callable because speak has been modified. Speak has been modified to a string value instead of this actual function that we would have needed. So that if I run just checking the speak attribute, I get boo. I mean, abstraction is good, but hold on a second here. This is bad. If I have a class that I've abstracted away, but anybody can come along, any programmer can come along and just remove all my hard work and overwrite it like that, isn't that bad? Let's take a break and explore this topic a little bit more in the next video. Welcome back. In the previous video, we saw that we did some big boo-boo. That is, we overwrote name and speak, and now all that hard work that we put into our class has been overridden by this. I mean, sure, if we instantiate a new object, we will have our run and speak, but player1 now is completely useless. It has no name and speak, well, it just says boo. Completely useless. Now in Python, there's this idea of public and private. And this is related to our discussion of abstraction. The idea behind abstraction is that we hide away information and only give access to things that a user is concerned about, right? So ideally, we shouldn't have access to init. Ideally, we shouldn't be able to, let's say, modify run or modify name and age, because when we create a player character in our game, hopefully the player can just randomly change their name or their age and sneak into our game that perhaps is only 18 and over. So can we make a private variable in our class? Well, here's the thing. Some languages allow us to have private variables. For example, in a language like Java, I can actually say that an attribute is private like this, and I won't be able to access it and modify it like I have this way. But in Python, there's no true privacy, no true private variables. So how do we get around this? Well, what we would do is do underscore name or underscore age. Now, does this give any special power? No, this is just a convention. That is, as programmers, as Python programmers, we determine that, hey, if we see underscore in our code, that most likely means that this should be a private variable. So that when I use it in speak, let's say underscore name, underscore age, and let's comment this out. If I click run, well, I have to run this because now it's a method. Let's click run. And I get my name is Andre and I'm 100 years old. It all works. But if I try to overwrite these and click run, oh, and now because it's no longer a method, let's remove speak, and I click run, this still works. And that's because, like I said, there's no true private variables. As programmers, we've decided that underscore means that you shouldn't touch this. Please don't touch this. You could still be bad and do something like this, but I'm letting you know ahead of time. If you see underscore, this shouldn't be modified. This should be private. And that's how we achieve privacy in Python. We all kind of agreed to say, hey, let's keep this little thing private. So if you ever want to keep a method or an attribute private, you just put an underscore in front of it, but it's no guarantee. What about this double underscore init? Again, this is something we're going to be speaking about very shortly, but it's called a dunder method. That is, it's built into Python. And we usually never write our own dunder methods. We would never write double underscore like this. These double underscores, and there's lots of them, have special meaning in Python. And the reason that they're named like this is because they're saying, hey, if you're writing double underscore for your variable, you're doing something very wrong. You're about to overwrite something. So once again, this double underscore is also a convention to let people know you shouldn't really touch this or modify this. With each data type, let's say a list, if I do dot, you'll see that as you scroll down, you have a lot of these dunder methods. Again, something that we're going to talk about. But these are here to let you know, don't overwrite these. If you're doing something like underscore, I don't know, doc, like this, that's bad. Don't try and modify it and assign it to 5. So this idea of a private field is important to Python. And although we can overwrite a lot of things, it's bad practice. But let's bring it back to abstraction. The idea is to abstract away this code. And although it can be modified and overwritten, by using these proper conventions like private attributes, we're able to abstract things away but still make sure that whatever the user might be using isn't going to break our code. I'll see you in the next one. Bye-bye. So we've talked about encapsulation, about abstraction. What about the third pillar of OOP? It's called inheritance. An inheritance allows new objects to take on the properties of existing objects. So you can inherit classes. Let's have a look at an example. Let's remove the previous code that we've had and go back to our game example. We want to create a new game, and we have different types of users. So we have users that can be wizards, that can be elves, that can be, I don't know, archers. But all these users have some common functionality, and each one of the sub-users, like wizards, elves, archers, have some common shared functionality, but then again, different maybe attacks. So using OOP, we can actually do inheritance. For example, let's say we have a class user here, and this user will have, let's say, a sign-in function or sign-in method. Once again, it's going to receive self, and then we'll just, for now, assume that we have some sort of a sign-in here. So let's just say for now, print logged in. Because in order to play a game, they have to be logged in. Okay. Now, you might be wondering, where is the init method here? Shouldn't we have that init method that gets run first? Well, we could. But if we don't have any variables or attributes that we want to assign to the user, well, in that case, we wouldn't need an init method. So for now, we'll just say that we don't need, there's nothing that the user has other than this sign-in method. Now, let's say we want to create a bunch of subclasses so that we have a class wizard. And for now, we'll just do a pass here so that we don't have an empty class, but it will still allow us to build it. And then let's say we also have a class archer that will pass through as well. Oh, and make sure we have brackets here. Now here's the thing. Ideally, all these wizards and archers are users as well, right? So we have users, and these users can have multiple forms. They can be wizards, they can be archers, they can be ogres, all the characters in our game. But all of them, let's say, have to be signed in first. How can we make sure that all of these users or classes also have access to sign in? Well, we can use inheritance. And how do we do inheritance? Quite easily, actually. All we do is in the bracket pass the parent class that we want to inherit from. So let's say I do user here. Now let's click run here. No errors, everything is looking good. And by the way, you see the green line here? Tells me that indentation is not a multiple of 4 because indentation should be 4 in Python. So we can just do this, but I like keeping it smaller just so it's easier to read. Okay, so let's instantiate a class here. I'm going to create a wizard1 and then say wizard and run that wizard class. Now, if I do print here and I do, let's say, print wizard, if I click run, I see that the wizard object has been created. And what if I do dot sign in? I see that, yeah, it's actually there. If I do sign in and click run, hey, I'm logged in. How cool is that? I inherited from the user class this functionality. And this is really, really powerful because now I can extend my wizard, right? So let's say that this wizard has an init method, which will be run when the wizard is created, and we'll have a name and power that we get. And in here, we'll assign self name to equal name, and then self dot power to equal power. And let's also add another method, calling it attack. And this attack method will simply print an f string that will say attacking with power of, let's say, self.power. And then we're going to do the same for the archer. So I'm going to copy this code, paste it in here, and the archer will have name. And let's say instead of power, we'll say that it has, let's say, number of arrows. And number of arrows will be the new attribute that it gets. And then the attack will have, well, attacking with arrows. And then we'll have arrows left. And arrows left will just say number of arrows. And we can do something fun where the arrows decrease as every time you attack. Okay, so now that we have this, let's make this a little bit smaller just so you can see. There you go. Now that we have this, let's instantiate the first wizard with, let's say, Merlin with a power of 50. And then the archer will be instantiated as Robin with, let's say, 500 arrows. Or let's do 100 arrows. So now, the wizard and the archer are going to have, well, they'll have the sign-in, but they'll also have the attack, but unique to their individual classes. And they'll also have different properties. Let's have a look. If I was to do wizard dot, let's do wizard 1 dot, and then we'll say attack. And let me just turn back my code intelligence. We'll see that we have a few errors. Here, what's it say? Undefined name, self, and that's because I forgot self in the brackets. So you remember, we always have to give the first parameter self. If we scroll down, we go to wizard dot, we see that we have name, power, and attack. If I click attack here and I run, we see that I'm attacking with power of 50. If I do archer 1 dot attack, in that case, I'll get attacking with arrows. Arrows left, 100. But both of these have the sign in function at the same time. How cool is that? This is the power of inheritance. We're keeping our code dry, right? We're abstracting away the part of the code that they both share, but then changing things according to what each one needs. So for example, I could have different methods and properties on wizard than the archer, but also have shared user functionality that they have. And this way it keeps our code organized and clean. Now let's bring back the zoom in just so you can see it clearer. Now, this idea of inheritance is really, really powerful. And the key here is that we have a parent class and children classes. Now, sometimes these children classes are called subclasses or derived classes because they're subclasses of user or derived from the user class. Let's explore this topic a little bit more in the next video. Now, I'm going to minimize this a little bit just so we can see a little bit clearer. It's not as messy this way. And I'm going to remove some of the spacing in between here, even though it'll give us a warning, just so we can see everything. There we go. All right, so we have these classes. Now, Python gives us a useful tool to check if something is an instance of a class. And easily enough for us, it's called instance or isInstance. And isInstance is a built-in function in Python. We give it the instance and then the class that we want to check. So in our case, if we had wizard 1 equals to wizard Merlin with power of 60, in that case, if I do wizard 1 and then do class wizard, and I print this, what do you think we'll get? If I click run, I get true, because wizard is an instance, or wizard 1 is an instance of wizard. Let me ask you this. What if I do user? Is wizard 1 an instance of user? Guess what's about to happen? It's true, right? Because wizard class is a subclass of user. So technically, yes, wizard 1 is an instance of user because we've had to run this class to create wizard 1. But here is the interesting part. If I do wizard 1 dot, do you see how I have our methods and attributes that I've added, but also all these dunder methods that we haven't really talked about yet? Where do these come from, right? Well, in Python, remember how I said everything is an object? Well, everything in Python inherits from the base object class that Python comes with, and it's called object. You see how it got highlighted here? So if I do isInstance wizard1 of object, oh, and I have to remove the dot over here. Let's click run. It's true, because wizard1 inherits or gets methods from the wizard class, from the user class, and even higher up from the object base class that Python comes with. And that's why we have these automatic methods attached for us, so that using object, every single method that is useful. For example, if I open up a list, if I do dot, and let's say we pick the REPR method, which we don't really know what it does yet, but if I go to wizard1 and I do dot, you see that I have it as well, because they both inherit from the object base class. And this way, we avoid repeating code. Any common functionality, I can just dish it out to all the objects that need it, which is very, very cool. So underneath the hood, when I do something like user, it's actually accepting object as the parent class in order to accept these properties that are built in and that we might need in the future. All right, that was a lot. One more pillar to go. I'll see you in the next video. Bye-bye. One final pillar of OOP to go. We talked about encapsulation, about abstraction, and about inheritance. And then there's this fourth one that has a pretty tough word: polymorphism. What does that mean? Well, poly means many, and morphism means form. So many forms. Now, we know that methods belong to objects, right? We use the self keyword to act upon the object that got instantiated. Now, in Python, this idea of polymorphism refers to the way in which object classes can share the same method name. But those method names can act differently based on what object calls them. Now, that sounds extremely confusing, so let's have a look at a code. We have our user, wizard, and archer classes. And as I mentioned, with polymorphism, different object classes can share method names. So we have attack here that is shared, but each one does something different based on the attribute. For example, when I do wizard1 attack, so let's do that, wizard1 dot attack. If I click run, I get attacking with power of 60. Because Well, wizard has a special meaning to its attack versus archer. They're different. So although they share the same method names, because of the object that's calling it, the output is going to be different. So we can actually do something quite interesting here. Let's say that I have wizard 1, and then we'll also have archer 1, and archer 1 will be Robin, and Robin has 30 arrows now. What I can do here is actually call them in different ways. For example, I can create an entire new function called player attack. And this player attack takes a character, and in here we can say character.attack. And now if I run this code and say player attack wizard 1, and I run this, I'll get attacking with power of 1. If I do player attack, have archer in here, if I click run, you see that the same function gives me a different output, even though we're calling the same thing because of the object that we pass into it, polymorphism. Another way to demonstrate this is if we do a for loop. If I do for, let's say, character in, and let's add wizard 1 and archer 1 into a list. And if I print here, or let's just run character.attack. If I click run here, once again, I have two different outputs, even though I'm calling the same method because of the different objects. And this is a really powerful concept, right? Because we're able to customize this according to our specific needs. Even if, let's say that the user had a attack method, and this default attack method is, let's say, print do nothing because it's just a user. Even if I run these, and let's say print wizard 1, and let's say dot attack, if I click run, it's going to override whatever the original attack was because we already have that method in our wizard class. But let's say I wanted to have both user and wizard run the attack method. How can I do this? Now, this is something we'll explore a little bit more in the next video, but for now, I can say user.attack and give it self. Because I accept user as my parameter in here, and then I can run user.attack. So let's see what happens here. If I click run, I have do nothing and attacking with power of 60. So polymorphism allows us to have many forms. It is the ability to redefine methods for these derived classes, that is wizard and archer. And an object that gets instantiated can behave in different forms, in different ways based on polymorphism. And this is useful because we are able to modify our classes to our specific needs, but also not have to repeat ourselves in case we want to use something like attack from user inside of wizard. So there you have it, the 4 pillars of OOP: encapsulation, abstraction, inheritance, and then finally polymorphism. Now, no amount of videos or books are going to teach you exactly when to use what. However, the idea here is to understand that these powers exist with OOP. You're never going to say, oh, I need to implement polymorphism. No, most of the time you're just coding along, and it happens that you're coding in a way that emphasizes polymorphism. This is just the power of OOP. Although these are big words, at the end of the day, we've learned how to use them to structure our code in a way that is efficient and clean. And that's the whole point. It's all about organizing our code. Now, some of you may have been a little confused when I did this, user.attack self. In the next video, I want to explore this a little bit more. I'll see you in that one. Bye-bye. Welcome back. In the previous video, I showed you how to call a method from a subclass of the parent class. So in our case, we did user.attack in order to run the attack method in user. Now, I've removed the attack method from now because I want to try something different. I want to create a init function in here. And this init function will take self, and then let's say that the user will receive, let's say, email. Because all the users of our game need to have emails. And in here, we'll just say self.email will equal the email. Nice and simple. Now, in here, if I was to run this code, and let's remove user.attack for now. So we have the same wizard. We've just added this init. And we have our wizard1. So if I run wizard here, and let's say we want to run wizard1.email. If I click run, I get wizard object has no attributes email. But I thought the user is going to be called when we create the wizard, right? When we instantiate wizard1. Well, the thing is, although we might inherit, let's say, for example, if I do dot, we might inherit the sign in from the user. And if I click run, we see that we inherit that. The wizard already has an init function, already a constructor, right? So how can we solve this? Well, one way is to just add email here, right? And just have the email attribute just right down here. But what's the problem with this? Well, it's inefficient, right? Because if I create an archer class, I'll have to do the same thing. And when we know that all these attributes are going to be the same on all of our subclasses, we want to do it here. So what's a more efficient way of doing this? Well, we want to call the init method of the user from inside here, right? Because every time we instantiate a new wizard, well, this init function is going to be called. So the way to do that is to say user dot underscore underscore init, and then give it the self, and then email. And then the email is something that we pass in. So that if I did go down here, I can say merlin@gmail.com is going to be the email. So that now, if I do, let's say, .email for wizard1, and I click run, I get Merlin's email. Once again, all we did was we called the init method of the user inside of the wizard. So when we instantiated a new wizard, we ran this function, and inside of this function, we ran the user.init and passed in the email that we passed in as an argument in here. Now, this is one way of doing it, and then there's another way, and it's called super. And it's a keyword. As you can see, it's being highlighted here. And all we do is run super. And super is referring to the super class or the class above wizard, which is user. And this is actually a new addition as of Python 2.2. With super, we actually no longer need the self. So our code looks even cleaner. And all we pass is this. And if we click run, we still get the right answer. Super allows us to refer to user this way and not have to worry about passing self. Welcome back. I want to talk to you about this idea of introspection. And introspection in computer programming means the ability to determine the type of an object at runtime. What is runtime? That is, when the code is running, you can determine the type of an object. And it's actually one of Python's strengths. Because everything in Python is an object, we can examine, we can introspect an object and actually figure out what our code does as we're coding and then running. And Python allows us to do introspection and inspect these objects with some nice helper functions. This one function is called dir. And dir, well, if I run this, will give me all of the methods and attributes that the wizard instant has. So with a dir function, we give it an instance, and right away we get access to what it has access to. Well, we see that we have name, power, and sign in. Again, we have the sign in from the user, and then we have also attack from the wizard class. And this editor that I'm using, whenever I do dot, is actually using this ability of introspection to just list out these available methods for me, just like I have here. So this is really useful when you're trying to figure out what you have access to. But you may notice something here. We have a lot of these dunder or magic methods that we haven't really talked about. What are these and why are they so important? In the next video, we're going to tackle this question. I'll see you in that one. Bye-bye. You've waited a long time for this because I've avoided talking about these dunder magic methods for a long time. In this video, we're finally going to uncover what they do. Now we're able to see what our instance has as methods using the dir method. And we told you that these were inherited from our base object class. Now, these underscores are special methods. Remember how we have things like length, for example, that allows us to tell the length of an array. These are actually implemented using these dunder methods. They allow us to use Python-specific functions on objects created through our class. So let me show you what I mean. We're going to create a new class. And this is going to be a toy class. Now, in here, we'll define a toy and initialize it with self. Then we'll say that it has color and age. Now we'll say color equals to color. So these will be our attributes and age. Awesome. There's our class. Now, let's say we want to create an action figure. This action figure will be instantiated with toy, let's say color of red, and the age is, it's brand new, so it's 0. Now, if I use something like, let's say str that comes with this object, if I do str or action figure dot underscore underscore str, like so, and we print this, we see that we get this. It's the exact same thing as us doing str action figure like this. Look at that. These double underscore dunder methods are special methods that Python recognizes. For example, the dunder str, this special method, allows us to use action figure like this using the str built-in function. As a matter of fact, if you go to the Python documentation under the special method names section, you'll see that we can do basic customizations of these dunder methods. And it's a long list of all these dunder methods that we can use. Now, don't go and read every single one of them. There are a lot, and you're not going to use them that often. There's only specific few cases that you're going to use them, and the idea is to know how to modify them and how they work underneath the hood. So let's go over a few examples. For example, let's modify what the str does. I'm going to define my own str here. I'm going to call self. And then in here, I'm going to return something different. I'm going to return, let's say, an f string that is, let's say, self.color. If I run this, I get red. Remember how I said not to modify dunder methods? Well, sometimes you're allowed to. Maybe there are cases, special cases, where you want your class to behave a certain way. Just like dictionaries, lists, tuples, and all our objects in Python can behave in certain ways. How lists were accessed with an index number and a dictionary was accessed with a key. Those are all implemented using these dunder methods. And you see here that because we modified this, the str now returns red when being called on action figure. It doesn't change things other than within action figure. If I run this, you'll see that it still runs action figure like this because this is a string. The str is only modified when we use it on this specific object. Like so. What other neat things can we do? Well, we can change the meaning of the length as well. So length, I can say self. And in here, I can just return 5. Now, if I print length of action figure, and I click run, I get 5. Very cool. By the way, if this underline is getting a little annoying, which frankly, for me, it's getting a little bit annoying, I'm going to click on settings here and just remove the code intelligence. So it won't tell me when my code is wrong, but hopefully we can just debug it ourselves. All right. So there we go. We've just changed the length dunder to return 5. Let's keep experimenting. We can also do something like __ delete. And delete, well, lets us actually use the delete keyword, which we actually haven't seen before. Delete, we can just say return deleted. You have to go like this, and let's just do print here, print deleted. If I click run, I see that I returned deleted. Now, the delete keyword I haven't really taught you because it's not something that you'll see a lot of. Usually this can cause some funny bugs in our programs that I like to personally avoid. But the delete keyword deletes some sort of a variable that we might have had in our program. All right, what else is there? Let's change this to use something called call. And call is an interesting one. Let's say that with call, we're going to return, and let's say yes, question mark. The neat thing about call is that now it gives our toy class some superpower. We can say action, figure, and then say, well, with call, we actually can now call the actual object with these brackets. So using call, I have this special way to call a function, which by the way, underneath the hood, the way we're able to call functions is using this dunder call. And if I click run, I get yes. How cool is that? All right, one last one because I think you're starting to get the idea of this. Like I said, these are all available in here. Usually you don't want to overwrite them, but you just want to know that you have the power to do so if you choose. The next one is called get item. So let's do define get item. Again, we're going to use self as the first parameter, and then let's say I for index. And in here, we'll return self dot, and let's add an attribute before we add that. I'm going to say self dot my dict for my dictionary, and then add name equals to yo-yo. And let's do has pets equal to false. Now, using this, I can say my dict and return the item based on the index that we give it. So let me show you what I mean. If I now do print action figure dot, and in here, instead of doing the dot, we do the square brackets, just like we would access perhaps getting a dictionary item. We can now, using the get item, say, what properties do we have? Name. So let's say name. And if I print this, forgot to add a comma in here. Let's try that again. And if I scroll down, you can see I'm really good at reading errors. Name error. Name action figure is not defined because it's action figure, not figure. That's better. Look at that. My name, Yo-Yo, was being able to access using this bracket notation, using the get item dunder. Very, very cool. So these special magic methods are really interesting because it allows us to do some custom modifying of our classes. And you can also understand how in Python, our built-in default types had access and abilities to have all these special syntaxes. We now have that power as well. Let's take a break and do a bit of an exercise. I have a fun little exercise for you. I want you to create a super list using the class superList. Now in here, I want you to add code that allows us to have, just like we have a list in Python, allow us to access through index, through, any way that a regular list allows us to use it. But the only difference is that the superList is going to have a special dunder method. Let's say that when we do length, so when we define dunder length, we're going to modify it and we're going to have it return no matter what 1,000. Now, this may look easy because all we want to do is modify the length dunder here. But the question is, based on what you learned about inheritance, about object-oriented programming, instead of having to write every single dunder that we need to use on a list, how can we easily acquire the power that list already has and then just modify this length dunder? So remember, superList is going to be a list that we can create, we can instantiate like this, superList1. We're going to call superList, and it's going to allow us to do things like length, superList, and also access items in the superList or use superList one dot, let's say append, and maybe append 5, and actually get superList1 5. All right, take it away from here, give it a go, pause the video because I'll give you the answer. So let's just implement this. We're going to have self in here, and we're only going to return, let's say, 1,000. So that when we call superlist1, and let's comment this out, and I do length here, let's print it out, I should get 1,000. That's good. But I want the functionality of this. I want to be able to append to my superlist. So let's run this and see what happens. I get an attribute error. Superlist object has no attribute append. Let's think about this. How can we acquire the powers that lists in Python already have? Well, we learned about inheritance, right? And all we have to do is just simply type list here. And now list becomes our parent class of superclass. So let's give this a go now. If I click run, all right, that seems to work. What if we want to access superlist at index, well, not 5, at index of 0? If I click run, I get 1,000. Well, that's because we're not printing anything yet. So let's print here and click run. Check that out. We're able to have this super list, and we just extended the functionality of list. How cool is that? Now, to double check, there's a fun little function that we have in Python, and it's called isSubclass. And here we say super list and list. If I click run, I get true. Because is superlist a subclass of list? Yep, that's true. What about this? Is list a subclass of the base object? Yep, it's true. Remember, everything in Python is an object that inherits from the base object class. We then inherit some built-in list methods, and we're able to use all of that in our super list just by inheriting like this. Very, very cool. Now, for some of you, this might have been a simple exercise and you got it right away. If you didn't, don't worry. Now you know. Pretty cool, eh? I'll see you in the next one. Bye-bye. Let's talk about multiple inheritance, which you're able to do in Python. Now, remember we have our user, wizard, and archer classes. We're trying to build that game, right? Now, let's clean up some of this code. We won't need the init function anymore. We'll just have user here. We have wizard that inherits from user, and also archer that inherits from user. But what happens if we want to create a new character? And this character is called a class, let's say it's called Hybrid Borg. A weird name, I know. But here's the thing. Hybrid Borg is a special type of character because it has the powers that wizards have, which is attack. It has the power that archers have, which is check arrows. And just for fun, let's also add run here. And we'll just say for run, ran really fast. All right. So we want this Hybrid Borg to have all of these methods. Can we do that? Well, we can. All we need to do is say wizard and then archer. We can give it as many parameters as we want as multiple inheritances. We're inheriting from wizard and archer. So that in here, let's say I don't do anything and I'll just hit pass. If I instantiate, let's say Hybrid Borg 1 is going to be Hybrid Borg class instantiated, I can now use all of these things. Let's check them. Let's say print hp1.run. Can I do that? And again, a little spelling error. Let's make sure it's Hybrid Borg, not Hybrid Board. I hope you're not bored of this video. All right, I get an error, missing 2 required positional arguments, name and power. All right, because, well, we have to pass these things in, right? It accepts these parameters. Okay, so let's say that we want name to be Borgie and the power to be 50. If I run this, all right, it looks like ran really fast. Run works. I was able to inherit from Archer. What about check arrows? If I click run, oh, I get hybrid Borg object has no attribute arrows. Now, why is that? Because technically we inherited from wizard first, then Archer. And wizard accepts name and power, but we never gave the arrows, name and arrows. So how can we solve that? Let's try something. Let's say we added arrows here, 100. Would this work? That doesn't work, does it? And this is a tricky thing with multiple inheritance, and why some programming languages actually don't even allow multiple inheritance. Things can get a little tricky because in your head, you have to make sure that you understand how these classes are implemented and make sure that we're not overriding anything. In our case, we can complicate our code a little bit. So what can we do here? Well, in here, I can perhaps do something like this. I can say define init. This receives self. It will receive a name, a power, and also arrows. And then finally in here, I can say that we're going to call also the Archer dot init, and that's going to take self and then pass in the name and arrows, so that if I run this, well, let's add the arrows, 100 here, and I click run. There you go. Arrows is now working. Now, just to check that our attack on the wizard is working as well, if we do attack and click run, oh boy, now our hybrid object has no power. So once again, in order for us to have power, we'll have to copy this, and let's say this time, wizard init self, and then give it power. If I click run, all right, attack works. Let's go back to check arrow, make sure we haven't broken anything. If I click that, that works as well. And then finally, what about sign in? Will sign in work? Logged in. All right. Oh boy, that was a lot. And there are a few ways of actually solving this problem. What I wanted to show you though, is that when you do multiple inheritance, things can get complicated. And although we walk through it step by step, imagine if there was a coder that came along on your team at work and tried to understand this code. Where we've added quite a bit of logic here and things are getting more and more complicated. And it's hard to keep track of everything in your head. And this is why multiple inheritance is one of those things where it's really, really powerful. But with great power comes great responsibility because we're creating more and more complexity. Again, part of the reason that some programming languages don't actually allow you to do multiple inheritance. And by the way, I'm going to confuse you even more. In the next video, we're going to talk about something called MRO. And it's going to be another great example of why you want to be cautious with multiple inheritances. I'll see you in that one. Bye-bye. Let's talk about something that sounds quite complicated. It's called MRO, or Method Resolution Order. What does it mean? Well, I have an example here for you. Let's say we have a class of A, class of B that inherits from class of A, does absolutely nothing. And then we also have class C that inherits again from A, and then finally a class D that inherits from B and C. So we have two classes that do absolutely nothing, and then a class A and class C that have the same class object attribute. And I've actually drawn out how this relationship looks like. You see that D has multiple inheritance from B and C inherit from A. And MRO, or method resolution order, is a rule that Python follows to determine when you run a method, which one to run. When you have such complicated inheritance structure, MRO is a rule that says, hey, do this, and then do that, and that's the method that you should run. Let me show you what I mean. Let's say I wanted to do print d.num. What do you think will happen here? Let me move this out of the way or comment this out. If I run this, can you guess what's going to happen? If I click run, I get 1. Is that what you expected? Let's look through this. D inherits from B and C, and then those inherit from A. So we get 1 because the MRO, the method resolution order, is that it doesn't go D, B, A. Instead, it goes D, B, C, A. Let's think about this a little bit more. MRO is simply saying what's first in line. If things are common between classes, methods, or variables or attributes, what should I pick? And there's actually a good way for us to check this. If I do MRO and then run it like this, if I click run, look at that. This is the order or the MRO of this class. It says, hey, I'm going to check D first. If you call, let's say, d.name or d.num, I'm going to check main.d first. So I'm going to check this class. Then I'm going to check main.b. So I'm going to check B. And then I'm going to check C. And then I'm going to check A. And then finally, I'm going to check the base class object. Again, we've seen that before. It's the base class that all objects in Python inherit from. So that's the order that it checks for num. If we pass all of these, and I click run, I'll get an error. D has no attribute num because it went through all this path, even checked the base object, and never found num. If I did something like str, if I click run, this works because it goes all the way through the inheritance chain and then gets to the base object, and the base object actually has this. So it does an error out, and yep, you can use the dunder string. Now I found a great example here to show you why inheritances can be confusing and why things like MRO you might want to avoid, or at least be conscious of. So let's copy this code and let's just remove all of this. And we're going to play a little game. Now, this syntax looks like this. So this is the inheritance model of what we just created. Looks pretty confusing, doesn't it? So if we do M here, and we check the MRO, or method resolution order of M, what do you think the order is going to be? Pause the video here and try to guess what the order will be. Ready? Let's do m.mro. And by the way, another way of doing this is to use the dunder MRO. And let's print this. All right, let's check this. So the first thing we have is M. All right, we check M. And then we check B. All right. And then we check A. So we check A here. And then we check X over here. Then Y. Then Z. Then the class object. Is that what you guessed? Let's look at the code. Why this order? Well, the order is because of the way that we're passing in the parameters. You see, B is passed before A and Z. So that means the order of MRO is going to be B, then A. But hold on. After B and A, what was that? Well, after B and A, we have class X. Why did X come before Z? So instead of going to Z, let's make this a little bit bigger. Instead of going to what we would have thought would be Z, it goes to X, then Y, then Z, then the object. This is because of the algorithm that they use for doing MRO, which is called depth first search. Now, this is beyond the scope of the course. But as you can see, it's quite a bit confusing. And as a matter of fact, Python actually changed the MRO rules from what we had previously in younger versions of Python. So this is another one of those things that got updated. But the reason I'm showing you this is because you're never going to get tested on this stuff. If you're writing code where the inheritance looks like this, I argue that you're writing bad code because this is overly complicated. We haven't even written any code actually inside of these classes, and it's already confusing. So MRO is there as a way to define what order you're going to inherit in, and you can always use the MRO function or dunder to check this. But the reason I brought it here is not just trying to confuse you. The reason is that it exists, however, you should not structure your code in this way. This doesn't mean that this doesn't happen in the wild. Yes, it does. But at least you have a way of checking and maybe debugging your code when you see a problem like this. I'll leave a resource for you about MRO if you're really curious and you really want to understand how this algorithm works and how this order is actually determined. But the key takeaway is that this is the way that Python works to determine, hey, when you call a method or an attribute, this is how I'm going to look up the hierarchy of inheritances. All right, if your brain hurts, don't worry, so does mine. Take a break, and I'll see you in the next video.